For the longest time, space was silent. That's because the universe is really, really quiet. Most of the time when we hear sounds, it's because some object is vibrating, disturbing the air molecules around it and making them collide with each other. Those collisions send signals to our ears, and our brains interpret those signals as noise. But there's nothing like that in the vacuum of space. Sound literally cannot travel there. So while we were listening for whispers from the universe, we were listening for something else. Radio waves. And they can carry information. But for a long time, the only radio waves we detected came from the instruments we put up into space to listen for them. Then in 2001, Parkes, an Australian radio telescope, detected a strange signal from billions of light years away. It lasted less than a second, but in that instant it released more energy than our sun does in 30 days. For a moment, the signal was 50 times brighter than an ordinary galaxy. At first, the scientists who found it thought there must have been some kind of mistake. Maybe it was a malfunction in the telescope or interference from a human source. But after further investigation, they concluded that the signal really had come from deep space. The only problem was, nobody knew what to make of it. Over the next decade, several similar signals were picked up by various telescopes around the world. All of them seemed to be coming from very distant galaxies. All of them lasted for a few thousandths of a second, and all of them were incredibly bright. In 2012, scientists gave them a name: fast radio bursts, or FRBs. And since then, our understanding of these bursts has changed dramatically. First, it went from "what are those?" to "are those real?" Some scientists argued that FRBs weren't real phenomena at all, insisting that they were somehow produced by glitches in the telescopes detecting them. But today, most astronomers agree that FRBs are real. We think they come from magnetars, extremely magnetized neutron stars with a radius of only about 10 kilometers and a mass roughly twice that of our sun. To put that in perspective, if you took the core of our sun and squeezed it until it was 10 kilometers wide, it would have a mass like this one and a magnetic field thousands of times stronger than Earth's. When such an object spins, its powerful magnetic field can accelerate charged particles to near the speed of light. As those particles reach the neutron star's surface, they release huge bursts of energy in the form of radio waves. But that doesn't explain why FRBs seem to come from all over the sky. If they're produced by spinning neutron stars, you'd expect them to come from relatively close to Earth, right? Well, yes, most of them do. But some have been detected in very distant galaxies, billions of light years away. What's more, their brightness suggests that they're extremely powerful. Even though they're incredibly faint by the time they reach Earth, astronomers can see them billions of light years away, which means they must be thousands or even millions of times brighter than the typical supernova. In other words, even though they last for a tiny fraction of a second, FRBs can briefly outshine entire galaxies. And despite their incredible power, astronomers have only managed to detect them about 20 times since 2001. That's because they seem to come and go quickly. Most astronomers think the bursts we've detected are only the ones that happen to be pointed in our direction. Since the universe is big and space is curved, we can't see most of the sky from Earth. We can only see a thin slice of it. So unless a burst just happened to be pointed at us, we wouldn't have seen it. That SY detecting fast radio bursts is like trying to hear a whisper from across a crowded room. There are just too many potential sources of noise drowning out the signal. And that's also why studying them is proving to be so difficult. Scientists don't know where the bursts are coming from or what exactly causes them. Some argue that they come from the same kind of magnetars that produce soft gamma repeater bursts. Others say they come from collapsing neutron stars or from matter falling into a black hole. But we won't know for sure until we detect one in time to see where it came from. However, one day soon, we might not need to hear the whispers of space to understand its language. There are already plans for space-based telescopes dedicated to listening for them. And if we can hear them from Earth's orbit, it will mean we'll finally know exactly where they come from and what makes them tick. In the meantime, though, we can keep listening to the silent music of the spheres and wondering what secrets the universe is whispering to us. You've heard some of the universe's most mysterious whispers, but what about its roars? This is an epic story of astronomical discovery, the search to understand one of the most energetic phenomena in the universe. Our story today takes us back to the year 2017. A team of Chinese astronomers working with the Fast Radio Telescope were scouring the skies for fast radio bursts. In just over a month of observation, they captured 16 bursts, and it seemed like they had found a pattern. Many of these bursts came from the M81 galaxy, around 30 million light-years from Earth. M81 is a relatively nearby spiral galaxy with a supermassive black hole at its core. All of this was interesting, but it was nothing compared to what happened next. One particular source in M81 stood out. It wasn't just sending out random bursts. Instead, the source was producing a repeating pattern of bursts, a sort of celestial Morse code. The repeating nature of this source gave scientists a precious clue to the origin of these bursts. Previously, scientists had speculated that the one-off FRBs might be caused by extreme events like the merger of two neutron stars. But mergers shouldn't produce regularly repeating signals. Something else was going on here. With this new discovery, scientists now had enough evidence to start exploring potential explanations. Their best guess was that these bursts were coming from neutron stars, highly dense remnants of dead stars that can spin and rapidly accelerate charged particles emitting huge amounts of radiation. Specifically, they thought the neutron stars might be in orbit around another compact object, such as another neutron star or a black hole. As the neutron star moves in its orbit, it would be alternately accelerated and decelerated by the gravitational pull of its unseen companion, sweeping its beam towards and away from Earth each time. And when the beam hit Earth, we saw a fast radio burst. This theory made sense in many ways. Neutron stars are known to emit beams of radiation. They are also capable of accelerating particles to near light speed, and some of them are believed to be pulsars, spinning neutron stars that emit regular pulses of radiation as they rotate. So the idea that neutron stars could produce FRBs was already well established. The discovery of repeating FRBs simply reinforced this idea. Now, the challenge was confirming it. It wasn't easy. Trying to detect the next FRB is much like trying to pinpoint exactly where lightning will strike next. Except here, you're trying to detect a needle in a haystack. Literally thousands of bursts are thought to occur every second, each lasting only a few milliseconds. Yet despite the difficulty, astronomers were determined. They knew that the key to solving this cosmic puzzle lay in catching the next burst in the act. As days turned into weeks and months into years, the race was on to observe the universe with greater precision and accuracy. Then in 2019, a monumental breakthrough occurred. Two separate teams of astronomers announced they had detected repeating FRBs coming from within our very own galaxy. These discoveries provided an invaluable opportunity to study these bursts in greater detail. After all, observing distant FRBs is challenging due to their vast distances, which makes studying them more difficult. But these newly discovered galactic FRBs were much closer, making them easier to study. To investigate further, scientists used several radio telescopes around the globe, including the National Science Foundation's Very Large Array, to scrutinize the location of these bursts. Their goal was to identify the exact position of the bursts and determine if they originated from a single source. Finally, their efforts paid off. Fast radio bursts. Unlocking the secrets of a cosmic enigma. The cosmos is vast and enigmatic, filled with wonders that continue to baffle and amaze us. Among the most intriguing phenomena that astronomers have discovered in recent years are fast radio bursts, an extraordinary class of intense, millisecond-duration bursts of radio waves originating from distant galaxies. Since their first detection in 2001, FRBs have captivated the scientific community with their perplexing nature and potential to unlock secrets of the universe. In this exploration, we will delve into the depths of FRB research, examining the latest discoveries, ongoing investigations, and the challenges that lie ahead. Join us as we uncover the mysteries surrounding these celestial explosions and the groundbreaking efforts aimed at comprehending their origins and implications for our understanding of the cosmos. Once the existence of fast radio bursts was established beyond doubt, astronomers quickly turned their attention to the next, and perhaps more important, question. What is producing them? The catalog of detected FRBs began to grow. With each new observation, subtle differences emerged. Some were brighter, some weaker. Some lasted a fraction of a millisecond, others stretched for several milliseconds. But one property above all began to divide them into two categories: repeaters and non-repeaters. The first repeater in 2012, the giant Arecibo radio telescope in Puerto Rico, famous for its contributions to pulsar astronomy and planetary radar mapping, recorded a burst unlike any seen before. This FRB seemed normal at first, a bright millisecond-long radio flash heavily dispersed, coming from far outside the Milky Way, but then, in 2015, the same location flared again, and again, and again. Astronomers realized they had found the first repeating FRB, cataloged as FRB 121,102. Unlike the one-off Lorimer burst and others of its kind, FRB 121,102 was persistent. It was not a single catastrophic event, like a star being destroyed, but an object capable of producing burst after burst of energy without exhausting itself. This discovery was a turning point. If FRBs could repeat, they had to come from some astrophysical engine that remained intact after each emission. Theories ranged from highly magnetized neutron stars, magnetars, to exotic objects like quark stars, or even interactions near supermassive black holes. If RB 121,102 became one of the most intensely studied objects in the universe. Using the Very Large Array in New Mexico and other instruments, astronomers were able to pin down its origin to a dwarf galaxy about 3 billion light-years away. Even more intriguingly, it was embedded in a persistent radio source, perhaps a nebula or a supernova remnant, suggesting it might be a young, highly energetic magnetar. Over the years, FRB 121,102 has emitted hundreds of bursts, some clustered together, some spread over months. It remains a cosmic laboratory for testing theories of FRB origins. Magnetars and galactic evidence. While FRB 121,102 hinted at magnetars, it was only speculation. Until 2020, that year. Something extraordinary happened inside our own galaxy. On April 28, 2020, telescopes around the world picked up a blindingly bright radio burst from the direction of SGR 1935, 2154, a known magnetar about 30,000 light-years away. The burst was thousands of times brighter than any previous radio flare from a galactic source, and it looked exactly like an FRB. This was the smoking gun. For the first time, astronomers had direct evidence that at least some FRBs are produced by magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's S. These fields are so powerful they can twist and snap, releasing catastrophic bursts of energy. If a magnetar's crust fractures, or its magnetic field undergoes a violent reconfiguration, it could send a shockwave of plasma into space, producing an FRB in the process. But not all FRBs can be magnetars. Some repeat, some don't. Some appear in dwarf galaxies, others in massive spirals. Some are linked to star-forming regions, while others aren't. This suggests multiple mechanisms may be at play. One-off bursts and catastrophic events. Not all FRBs behave like 121,102. Many are non-repeaters, detected once then never again. These may represent entirely different phenomena. One leading theory is that non-repeating FRBs could be caused by catastrophic cosmic events, such as the collision of neutron stars or the collapse of a massive star into a black hole. These processes release enormous amounts of energy, but only once. If this is true, FRBs may be connected to some of the most violent events in the universe, similar to gamma-ray bursts. Other possibilities include interactions between neutron stars and black holes, or even the evaporation of hypothetical primordial black holes. Each of these scenarios could produce powerful one-off flashes of radio energy. Extragalactic bursts in cosmic distances. Perhaps the most staggering fact about FRBs is just how far away they often are. While the Lorimer burst in FRB 121,102 already hinted at extragalactic origins, more precise localizations have confirmed that many FRBs come from galaxies billions of light-years away. Consider this. For a telescope on Earth to detect such a burst, the initial event must have been unimaginably powerful. In just a few milliseconds, an FRB can release as much energy as our sun radiates in days, weeks, or even months. And yet, because they're spread across enormous distances, the signals arrive to us as faint blips, whispers on the cosmic radio dial. Astronomers have since cataloged hundreds of bursts, with a growing fraction successfully pinpointed to host galaxies. These range from tiny, irregular dwarfs rich in star formation to massive spiral galaxies similar to our own. No single host environment has yet explained them all. A puzzle in two classes, so today, FRBs appear to fall into at least two broad categories. Repeaters, like FRB 121102, linked to persistent sources and likely powered by magnetars or other ongoing astrophysical engines. One-offs, single bursts that may be catastrophic in nature, tied to cosmic events that occur once and never again. This division doesn't necessarily mean only two origins exist. In fact, the diversity of FRBs suggests that multiple astrophysical pathways may lead to similar signals. Magnetar flares, neutron star mergers, black hole activity, and perhaps other exotic processes may all contribute to the FRB population. What's certain is that FRBs have evolved from a single strange signal in archival data to a rich catalog of cosmic events. Each new detection refines the picture, showing us that these bursts are not a monolithic phenomenon but a window into a variety of extreme astrophysical environments. And yet, even with repeating bursts, magnetar evidence, and extragalactic origins, many mysteries remain. Why do some bursts repeat with irregular rhythms, while others never return? What physics determines the intensity, the frequency drift, and the polarization patterns seen in these bursts? And could some of these signals be evidence of something even more exotic, perhaps beyond our current understanding of physics? That takes us to the next stage of this cosmic investigation, the frontier of theories. The unresolved puzzles and the tantalizing possibility that FRBs may not only be astrophysical, but just maybe something stranger still. As our understanding of FRBs continues to evolve, so too does our perception of the universe itself. These enigmatic bursts challenge our preconceived notions about the nature of celestial objects and the forces that shape them. They remind us that the cosmos is replete with wonders that defy easy categorization and push the boundaries of our scientific comprehension. In exploring the intricacies of FRBs, we are simultaneously deepening our knowledge of the fundamental laws that govern the universe and expanding our appreciation for the boundless mysteries that lie at its heart. At the core of this enigma lies the pursuit of unraveling the mechanisms that give rise to these bursts. Scientists are working tirelessly to comprehend the physical processes that trigger and sustain them, ranging from the behavior of neutron stars and black holes to the properties of exotic matter and the nature of intergalactic space. Each theoretical model and simulation brings us closer to unraveling the truth behind these celestial explosions. Moreover, the study of FRBs has opened a new window into the realms of astrophysics and cosmology. By analyzing the characteristics of these bursts, including their dispersion, polarization, and host galaxies, astronomers are gaining insights into a myriad of cosmic phenomena. From the distribution of matter in the universe to the nature of dark energy, FRBs provide a unique perspective that complements other astronomical observations. They serve as beacons that illuminate the most distant reaches of the cosmos, allowing us to probe the evolution of galaxies and the large-scale structure of the universe. Furthermore, the quest to understand FRBs has spurred the development of cutting-edge technologies and instrumentation. The construction of advanced radio telescopes and the refinement of data analysis. Techniques have not only advanced our knowledge of FRBs, but have also yielded valuable insights into other areas of astronomy. The global collaboration and international partnerships that drive FRB research foster an exchange of ideas and resources that transcend national boundaries. It is a testament to the universality of scientific inquiry and the power of collective endeavor in pushing the boundaries of human knowledge. In conclusion, the study of fast radio bursts stands as a beacon of progress in our quest to comprehend the intricate tapestry of the universe. As we continue to unlock the secrets of these enigmatic celestial explosions, We unveil not only the nature of FRBs themselves, but also gain profound insights into the fundamental laws that govern the cosmos. From the behavior of exotic objects like magnetars to the properties of intergalactic space, FRBs serve as keys that unlock new vistas in astrophysics and cosmology. The journey of discovery has just begun, and with each new revelation we inch closer to unraveling the grand design of the universe. As we gaze up at the heavens, we are reminded of the boundless wonders that await our exploration and the endless quest for knowledge that drives humanity forward. FRBs may have started as a statistical curiosity, but they are fast becoming one of the most exciting research areas in astronomy. The future holds even more potential for discovery. With ever larger radio arrays coming online and ever more precise localizations of FRB sources, it won't be long before we learn which models best fit the data. And when we find the smoking gun that confirms the origin of at least one class of FRB, it will inaugurate a new era in our understanding of the universe. Are there intelligent beings out there watching us? It's a question that's occupied humans for generations, and now it seems we might have some evidence to answer it. In the past decade, astronomers have witnessed a surge in fast radio bursts, or FRBs, a class of extremely bright radio wave explosions originating from distant galaxies. These bursts are so powerful that if they were aimed at Earth, they could disrupt our global positioning system and even pose a threat to human health. But thankfully, they seem to be a rare occurrence. But what if they are actually a carefully crafted message? Fast radio bursts are short, intense pulses of radio waves that last only a few milliseconds. Despite their brevity, these bursts can release as much energy as the sun does in several days. Originally discovered in 2001, FRBs were dismissed as a potential interference in data from Parkes Radio Telescope in southwest Queensland. However, further investigation revealed that they were a new class of astronomical phenomenon. Since then, we've recorded almost 1,000 bursts. Each FRB is unique, varying in duration, energy, and repetition. But amidst this flurry of research, many questions remain unanswered. Are these bursts truly natural occurrences? Or are they a sign of an advanced civilization trying to communicate with us? It's a controversial topic, and some argue that we should remain cautious when considering extraterrestrial communication. But the possibility of life beyond our world is a question that has fascinated humanity for centuries. Who are we kidding? We want to believe. Let us explore the latest findings regarding fast radio bursts and their potential implications for the future of humanity. But first, if you find this video interesting, please stay tuned for more updates. One of the most intriguing aspects of fast radio bursts is their origin. While scientists have not definitively identified the sources of these bursts, there are a few leading hypotheses that attempt to explain their characteristics and behavior. The magnetar model posits that FRBs originate from highly magnetized neutron stars known as magnetars. When these stars undergo sudden magnetic reconfigurations, they release tremendous bursts of energy, which we observe as FRBs. Another popular theory suggests that FRBs are produced by cataclysmic events, such as neutron star mergers, supernova, or the collapse of a massive star into a black hole. These events release immense amounts of energy and could potentially generate the observed bursts. However, these models fail to explain why some FRBs repeat while others do not. Additionally, they struggle to account for the wide range of observed burst durations and energy levels. One more theory proposes that FRBs are produced by a process known as plasma lensing, where a large cloud of plasma distorts and magnifies the light from a background source. This model could explain the variability in burst brightness and the occasional appearance of multiple bursts from the same source. Now let's talk about the potential danger posed by these bursts. If an FRB were to occur within our planetary system, it could have significant implications for life on Earth. The radio waves emitted by these bursts are extremely powerful and could potentially disrupt important technologies that rely on radio frequencies, such as GPS and satellite communication. Moreover, the high energy levels associated with FRBs could damage the ozone layer, exposing Earth's inhabitants to harmful levels of radiation. While it's unlikely that an FRB would pose an existential threat to humanity, it could certainly cause widespread technological and environmental damage. Imagine being caught in the middle of nowhere without your phone or any way to contact help. It's enough to make anyone's skin crawl. FRBs have also raised concerns about their potential impact on exoplanet life. Given the vast distances involved, it's unlikely that an FRB would directly affect life on planets outside our solar system. However, the radio waves emitted by these bursts could potentially interfere with communication and other technologies developed by advanced civilizations. In fact, some scientists speculate that the rarity of FRBs could be evidence of the zoo hypothesis, which suggests that civilizations capable of generating such powerful bursts tend to destroy themselves before reaching interstellar communication capabilities. Despite the potential risks, FRBs offer an exciting opportunity for scientific discovery. By studying these bursts, astronomers can learn more about the fundamental properties of the universe, such as the distribution of matter and energy in the cosmos. One of the most promising areas of research involves using FRBs to probe the interstellar medium, the vast expanse of gas and dust between star systems. As the radio waves from FRBs travel through the interstellar medium, they interact with the particles in the medium, providing valuable information about its composition and density. This could help scientists better understand the formation of stars and planets and shed light on some of the most fundamental questions in astrophysics. Another exciting development in FRB research is the use of machine learning to identify and classify these bursts. Machine learning algorithms can analyze vast amounts of data and identify patterns that may not be apparent to the human eye. This could help scientists detect FRBs more quickly and efficiently, leading to a better understanding of these mysterious phenomena. The power of AI is truly remarkable, and I'm excited to see how it is being used to advance our knowledge of the universe. So what's the verdict? Could fast radio bursts really be an attempt at communication from an advanced civilization? While the idea is intriguing, it remains firmly in the realm of science fiction. There's simply no concrete evidence to support the claim that FRBs are artificial in origin. Moreover, the sheer number of FRBs detected in recent years, combined with their diverse range of characteristics, makes it increasingly unlikely that they are the result of a coordinated effort. Instead, the most plausible explanation for FRBs is that they are a natural phenomenon caused by extreme astrophysical events, such as supernova or the merging of neutron stars. While there is still much that we don't know about FRBs, it's important to remain grounded in scientific evidence and critical thinking. Extraordinary claims require extraordinary evidence, and there is simply no evidence to support the idea that FRBs are an alien attempt at communication. That being said, the possibility of extraterrestrial life is a fascinating topic that has captured humanity's imagination for centuries. And while FRBs may not be the answer to the question of whether we are alone in the universe, they do remind us of the vastness and complexity of the cosmos. Who knows what wonders and mysteries await us in the uncharted territories of space? Thank you for watching and joining me on this journey of discovery. Together, let's keep exploring the mysteries of the universe. Until next time, keep looking up. From the mind-boggling distances involved to the sheer power of these bursts, FRBs challenge our understanding of the physical laws that govern our world. But amidst the awe and wonder, it's crucial to approach this topic with a healthy dose of skepticism and scientific rigor. Extraordinary claims require extraordinary evidence, and it's up to us as rational thinkers to demand it. The allure of the unknown, the possibility of life beyond our world, is a siren call that has captivated humanity for millennia. It's easy to get swept up in the excitement of it all, to entertain the idea that these bursts are a message from an advanced civilization trying to reach out across the vast expanse of space. But we must resist the urge to jump to conclusions and instead focus on the evidence. Employing rigorous scientific methods, analyzing data, testing hypotheses, and embracing a spirit of inquiry is essential. Whether or not we ultimately uncover evidence of extraterrestrial intelligence, the journey of discovery is a testament to the power of human curiosity and our relentless pursuit of knowledge. So let us continue to explore the mysteries of the universe with open minds and a healthy dose of skepticism, always keeping in mind that the most extraordinary claims require the most extraordinary evidence. The search for FRBs is a testament to the spirit of scientific exploration. It took decades of patient work and technological advancement to turn a mysterious signal detected in old data into a confirmed object of study. Today, as dozens of new FRB candidates emerge and more sophisticated telescopes come online, scientists stand ready to uncover the secrets of these blasts from the past. The rewards promise to be profound, whether they come from unraveling exotic physics near dead stars or from hardening our technology against future space weather extremes. No matter what challenges lie ahead. The discovery of fast radio bursts reminds us of humanity's capacity to probe the unknown, turning potential threats into opportunities for learning and growth. Humanity's story is one of constant exploration and pushing the boundaries of knowledge. The discovery of fast radio bursts, an achievement of modern technology, data analysis, and international collaboration, is a prime example of our species' inquisitive nature. What began as an unexpected signal in archived data evolved into a full-fledged area of investigation thanks to the efforts of numerous researchers worldwide. This journey highlights the importance of curiosity-driven science and the power of global collaboration. The detection of FRBs is a remarkable feat of technology. Building highly sensitive radio telescopes capable of detecting faint signals from billions of light years away requires significant advancements in engineering and computing. The international team behind the Parkes telescope, led by researchers at the National Autonomous University of Mexico, epitomizes the collaborative spirit necessary to achieve such breakthroughs. Their innovative use of a relatively small telescope to detect FRBs showcases resourcefulness and ingenuity. The process of verifying the source of FRBs involves overcoming substantial technical challenges. Pinpointing the location of these bursts in the vast expanse of space necessitates precise measurements and sophisticated data analysis techniques. Astronomers utilize various methods to identify the host galaxies of FRBs, including utilizing dispersion as a tool to determine distances. These efforts not only expand our understanding of the universe, but also contribute to advancements in data analysis and processing, with applications extending beyond astronomy. The implications of FRB research extend beyond the scientific community. Understanding the origins and characteristics of these bursts provides insights into extreme environments such as magnetars and collapsing neutron stars. Additionally, exploring the potential impact of FRBs on Earth, while still uncertain, encourages the development of more robust space-based technologies capable of withstanding cosmic disturbances. The field of astrophysics continues to evolve rapidly, driven by new discoveries and technological advancements. Upcoming projects like the Square Kilometer Array and the Nancy Grace Roman Telescope promise to revolutionize our understanding of the universe by providing unprecedented sensitivity and observational capabilities. These developments will undoubtedly lead to further insights into the nature of FRBs and their significance in the grand scheme of cosmic phenomena. The search for extraterrestrial intelligence, or SETI, often captures the imagination when it comes to humanity's quest to understand its place in the universe. While SETI endeavors focus on the detection of artificial signals from distant civilizations, the discovery of fast radio bursts offers a unique perspective on our own technological achievements. The remarkable sensitivity and precision required to detect FRBs underscore the ingenuity and collaborative spirit of modern science. In an era marked by rapid technological advancements, the quest to understand FRBs exemplifies the transformative power of knowledge and exploration. As humanity continues to push the boundaries of what is possible, the discovery of these enigmatic signals serves as a reminder of our remarkable ability to unlock the secrets of the cosmos. The study of fast radio bursts represents a pivotal moment in our exploration of the universe. These powerful transient events originating from distant galaxies provide a unique window into extreme astrophysical phenomena and the evolution of the cosmos. The detection of FRBs has captivated the scientific community and sparked a new era of discovery. As we continue to probe the depths of space, the insights gained from FRBs will undoubtedly shape our understanding of the fundamental laws governing the universe and our place within it. The impact of fast radio bursts on our understanding of the universe is profound. The discovery of FRBs has opened up new avenues of research into some of the most extreme and enigmatic phenomena in the cosmos. The detection of these bursts has provided invaluable insights into the nature of magnetars, neutron star-powered outflows, and the behavior of matter under extreme conditions. Furthermore, the study of FRBs has highlighted the interconnectedness of the universe, demonstrating how seemingly isolated phenomena are often linked in complex ways. The quest to understand FRBs has fostered international collaboration among astronomers and researchers worldwide, uniting scientists from different nations in a shared pursuit of knowledge. This global collaboration has resulted in the construction of advanced radio telescopes and data analysis techniques that push the boundaries of our observational capabilities. As we continue to unravel the mysteries of FRBs, the sense of wonder and awe they inspire will continue to drive humanity's quest for understanding and exploration. The discovery of fast radio bursts has had a profound impact on our understanding of the universe. These powerful transient events have revealed new insights into some of the most extreme and enigmatic phenomena in the cosmos. The detection of FRBs has allowed us to explore the nature of magnetars, neutron star-powered outflows, and the behavior of matter under extreme conditions. Moreover, the study of FRBs has emphasized the interconnectedness of the universe, highlighting the complex relationships between seemingly isolated phenomena. The quest to understand FRBs has fostered international collaboration, uniting scientists in a shared pursuit of knowledge and advancing our observational capabilities. As we continue to unravel the mysteries of FRBs, their impact on our understanding of the universe will continue to grow, inspiring new discoveries and deepening our appreciation for the wonders of the cosmos. In conclusion, the story of fast radio bursts is one of scientific discovery, technological achievement, and the relentless pursuit of knowledge. From their initial detection to their identification as extragalactic in origin, FRBs have captivated the imagination of astronomers and the public alike. The study of FRBs has revealed new insights into the nature of magnetars, neutron star-powered outflows, and the behavior of matter under extreme conditions. It has also highlighted the interconnectedness of the universe and the importance of international collaboration. In advancing our understanding of the cosmos, as we continue to explore the mysteries of FRBs, their impact on our understanding of the universe will only continue to grow. These enigmatic bursts of energy serve as a reminder of the boundless curiosity and spirit of discovery that drives humanity forward. Whether peering deep into the heart of a collapsing star or searching for signs of life on distant worlds, are insatiable. Thirst for knowledge and exploration will continue to propel us toward new frontiers and deeper insights into the workings of the universe. The year is 2007, and astronomers are sifting through years of data collected at the Parkes Radio Telescope in Australia. It's tedious work combing through endless numbers, but someone has to do it. Just after 2 years of looking, they find something remarkable. An anomalous radio signal unlike anything they've seen before. At first they think it might be a pulsar, a neutron star that beams particles from its poles like a cosmic lighthouse. But no, this signal is too brief, lasting only a few milliseconds. It's a previously unknown phenomenon, an extremely bright but ultra-short burst of radio waves from billions of light-years away. They name it a fast radio burst. Today, a decade later, scientists know that these bursts are much more common than they initially thought. But despite the many they've recorded, they still don't know exactly what causes them. Astronomers have discovered a surprising variety of FRBs, some that occur only once and others that repeat periodically. Some come from galaxies similar to our own, while others appear to originate from galaxies with unusual properties. Yet despite the progress made in unraveling their secrets, there's still a lot that scientists don't understand about FRBs. For instance, astronomers do not know if all FRBs are created equal, or if they re-manifestations of different physical processes. That's because although FRBs have been observed across the electromagnetic spectrum, all of them are still quite rare. Most of the ones that have been recorded so far are one-offs and haven't been seen again. So scientists don't have enough data to definitively link any of them to specific galactic phenomena. And those that have repeated themselves, which account for only a tiny fraction of total FRB detections, are difficult to study. It's partly because they repeat at unpredictable intervals. For example, the first repeater discovered FRB 121,002 repeats roughly every 16 days. But another repeater named FRB 190,520, which was discovered in 2019, repeats every 47 days. Then there's FRB 121,002, which scientists once thought was a repeater, but they haven't seen it in over 6 years. If scientists want to learn more about these bursts and their sources, they need to detect and record more of them. That means developing new instruments and techniques to search for FRBs, which are brief, intense radio flashes that can originate from anywhere in the night sky. No one knows when or where the next FRB will occur. Scientists have had to get creative to develop sophisticated systems to comb through tons of data and flag promising candidates. They've also had to work together in unprecedented ways. The hunt for FRBs is becoming one of the most dynamic chapters in modern astronomy. Here's how we found them, and how we'll keep finding more. A tale of two telescopes in the early days of FRB research. Scientists used radio telescopes to continuously scan the skies, hoping to stumble upon a burst. Most telescopes can't do this because they spend most of their time focused on a particular target, but radio telescopes are different. So in 2007, when astronomers discovered the first FRB, they did so by analyzing archived data from the Parkes radio telescope in Australia. Parkes was designed to search for pulsars, highly magnetized remains of collapsed stars that emit beams of radiation as they spin. In the 2 years that it took to analyze the data, scientists missed the actual event by several years. It would be better if we could spot them in real time, but to do that, we needed bigger and more powerful instruments. In 2012, the Arecibo Observatory in Puerto Rico solved this problem by turning its 305-meter radio telescope towards the original FRB source for nearly a full year. After 427 days, the telescope detected the source flare up again. But this time it was over in less than a second. Scientists named this source FRB 121002 because it was the second FRB they had found, and it became the first repeating FRB. The discovery showed that FRBs could come from outside our galaxy. The fact that it was periodic suggested that the bursts originated from a compact object, such as a neutron star. Over the next 3 years, however, Arecibo found no other repeaters. Then in 2016, scientists reported the first extragalactic burst from a source located 3 billion light-years away. With follow-ups from other telescopes, they localized the source to a dwarf galaxy that was home to a supermassive black hole. The same year, they identified another FRB that also originated from a dwarf galaxy. These discoveries prompted scientists to focus on finding more repeaters. While Arecibo was hunting down FRB 121002, a group of Canadian astronomers were building an instrument to survey our universe. Their device, called CHIME, consists of 4 100-meter diameter reflectors shaped like giant letter CS placed inside the radio wave band. The receiver scans the sky roughly twice a year. When it finds something interesting, it can automatically send alerts to other telescopes around the world. CHIME began operations in 2018 and quickly surpassed the number of bursts detected by Arecibo. In just a few months, it recorded 1,652 FRBs, nearly twice as many as Arecibo had in nearly a decade. CHIME detects bursts that last just 10 milliseconds or longer. It can also quickly narrow down potential sources, making follow-up observations more efficient. Now that scientists have a much larger sample size, they can try to correlate bursts with certain galactic phenomena. But to do this, they need to identify the positions of the bursts and figure out where they're coming from. This isn't always easy. To improve their chances of pinpointing the sources, scientists are using a technique called multi-wavelength astronomy. The idea is to observe the universe at multiple wavelengths simultaneously. That way they can identify objects that might otherwise be invisible at a given wavelength. For example, in 2020, astronomers used data from the Chandra X-ray Observatory and the Hubble Space Telescope to detect X-ray and visible light emissions from one of the burst sources. The X-ray data helped them pinpoint the location of the source and estimate its distance. The visible light data showed that the source is located in a dwarf galaxy. Together, the telescopes were able to measure the rate at which the galaxy's light was redshifted, which indicated its distance. This technique has allowed astronomers to identify the host galaxies of some of the repeating bursts and study their properties. For instance, they found that the galaxy hosting FRB 121002 is highly magnetized and has an exceptionally powerful magnetic field. Such fields are thought to play a role in launching fast radio bursts. So, the discovery suggests that the bursts may be connected to the activity of the supermassive black hole at the galaxy S core. It could also explain why FRB 121002 comes from a relatively small galaxy. Another repeating source, FRB 190520, was identified in 2020 and appears to come from a magnetar, a type of neutron star with an ultra-strong magnetic field. Although scientists have only detected the burst once, they have yet to identify its host galaxy. However, they hope that follow-ups with ground-based radio telescopes will help locate it. Meanwhile, CHIME is continuing to discover new repeaters. For example, in 2020, scientists reported that they had spotted a new repeater that emits bursts every 16 days. This has renewed interest in FRB 121002, the first repeater, whose activity appears to have ceased in 2019. Could the two be related? We'll have to wait and see what further investigations reveal. The future of FRB research today. More than 2,000 FRBs have been detected, but scientists believe there are millions more out there. According to one estimate, for every FRB we see, there are 1,000 that go undetected. Most of these are probably one-off bursts that are impossible to track down. But that may not always be the case. In the future, scientists hope to use FRBs as tools to explore the universe. They already use FRBs to probe the intergalactic medium, the matter between galaxies. When an FRB reaches Earth, it can travel through clouds of gas and dust, allowing scientists to study the distribution of matter in space. But scientists think that FRBs can do much more. They are considering using them to image the interior of neutron stars and study the behavior of matter under extreme conditions. They are also exploring whether FRBs can be used to detect dark matter and dark energy. Some scientists even believe that FRBs could help them predict the heat death of the universe. There is still a long way to go before any of these futuristic ideas become reality. But one thing is clear. The discovery and study of FRBs has transformed our understanding of the universe. Who knows what other surprises await us in the years to come? Do you love space as much as I do? In 2007, astronomers were sifting through data from a Parkes radio telescope in Australia when they noticed something odd. A brief but intense flash of radio light that lasted only a few milliseconds and originated from billions of light years away. It was unusual, puzzling, and at the time, seemingly without any obvious explanation. Today, that event known as the Lorimer burst is now seen as the opening chapter in a new area of astrophysics. The study of fast radio bursts, or FRBs. These millisecond-long pulses of energy are the most powerful explosions in the modern era, releasing as much energy in a few milliseconds as the sun does in several days. Since that first detection, hundreds of FRBs have been found. But despite their immense power and intriguing nature, scientists still know relatively little about them. Many questions remain unanswered, and the true story of FRBs is still being written. What began as a scientific curiosity may turn out to be one of the most remarkable chapters. The discovery of FRBs was just the opening of a mystery. It was the unveiling of a new tool. At first, FRBs seemed like exotic curiosities, puzzling flashes of radio light with no clear explanation. But as astronomers have studied them, a profound possibility has emerged. These fleeting bursts might allow us to explore the universe in ways that were previously impossible. In other words, FRBs are not only strange, they are useful. FRBs as cosmic rulers, every FRB we detect carries with it the imprint of its journey through space. As the burst travels across billions of light years, it is slowed and stretched by the plasma it encounters, the thin gas of electrons and ions. It fills galaxies in the vast intergalactic medium. This effect, called dispersion, means that higher frequency radio waves arrive slightly earlier than lower frequency ones. The amount of delay is directly proportional to the total number of free electrons along the line of sight. By measuring the dispersion of an FRB, astronomers can calculate the column density of matter it passed through. In simple terms, each FRB is a probe, a measuring stick that tells us how much invisible matter exists between its origin and us. This is revolutionary because most of the universe's normal matter, the protons, neutrons, and electrons that make up stars, gas, and planets, is hidden. Observations of galaxies and clusters suggest that a large fraction of ordinary matter is unaccounted for. The so-called missing baryon problem, FRBs, may provide the missing map. A cosmic cartography: imagine thousands of FRBs scattered across the sky, each one a data point. Together, they could create a three-dimensional map of the universe's plasma content. This would allow astronomers to trace the distribution of matter in intergalactic space, test models of large-scale cosmic structure, and measure the amount of baryonic matter hidden in filaments between galaxies. Already, early studies have used FRBs to provide the first direct evidence that the missing baryons are indeed hiding in the warm-hot intergalactic medium, WHIM. With enough FRBs, the map will become more precise, offering a powerful new complement to galaxy surveys and cosmic microwave background studies. Probing fundamental physics, FRBs may also serve as laboratories for testing physics under extreme conditions. Because they travel across billions of light-years, they are sensitive to even tiny deviations in how different kinds of radiation move through spacetime. This means FRBs can be used to test Einstein's general relativity. Photons of different energies arrived at different times in a way not explained by plasma dispersion. It might hint at new physics. Constrained dark matter models. Some theories suggest dark matter could interact with photons in subtle ways. FRBs could provide limits on such interactions. Probe cosmic magnetism. The polarization of FRBs gives clues about magnetic fields in intergalactic space, a poorly understood but fundamental component of cosmic evolution. The square kilometer array in the future? The future of FRB science will be transformed by the Square Kilometer Array SKA, the world. It's the largest radio telescope project under construction in Australia and South Africa. With its unprecedented sensitivity and wide field of view, the SKA is expected to detect thousands of FRBs per year, providing a flood of data that will revolutionize the field. Other projects like upgrades to CHIME, the full operation of fast and new networks of small dishes around the world, will add to this effort. We are entering an era where FRBs will not be rare events, but routine astronomical tools. It's a strange irony that the study of FRBs isn't just about listening to the universe, it's also about learning to hear it in new ways. In an increasingly noisy world, this quiet revolution is a reminder of the power of observation and the endless wonders that await those who take the time to listen closely.